Okay, so we're going to go back to 8th grade for a day or two. Most of you all, when you picked up these notes after your test today, were like, oh, I remember how to do this, which is a good thing because we have to do systems of equations for a day or two to remind you so that we can do systems of inequalities. That's a standard for 9th grade. So we're going to take this systems of equations and kind of work our way to systems of inequalities over the next few days. Okay, systems of equations. That's our heading of our notes. System of equations is two or more equations with the same variables. Okay, y'all kind of know what that means.
That's a definition
of a system of equation. The good vocabulary part for when it comes for our next test. So, okay, there are technically three ways to solve a system. You can solve it graphically, which is the easiest, which is why we always do this way first. Then you can solve it algebraically, and there's two methods. They're the substitution method and the elimination method. Ms. Delkin, my favorite way is elimination, so we're going to do that last. We're going to save that one for last. But substitution is always a good method if one of your variables is already isolated. Okay, we'll talk about that when we get there. All right, types of solutions. There are three types of solutions. The first one is intersecting. Okay. She's writing you the two methods up there just so you have it. Okay, so substitution and elimination. And then graphically, and let's talk about this. Every time we solve a system, our answers are in ordered pairs. Notice that the definitions are a point where the two lines intersect. So if the two lines intersect, our answer must be a point, okay? And then we can always take that point algebraically and plug it into both equations and see if it's true. And remember that we're always looking for balance when we plug in. Does one side balance to the other? All right, now, Ms. Duck is going to draw you examples of intersecting lines. Notice we quickly drew us a little coordinate plane just so y'all could see it. All right, intersecting lines. You see they intersect at one point.
Therefore, they have one solution. And we write it as x comma y.
Okay, so the point at where they intersect. Okay, the second type of solution you could have would be parallel lines. And notice, watch Ms. Delk, she does this. It's a good little reminder. The two L's in parallel show you what parallel is. So she's going to draw a pair of parallel lines. And think about when you're solving systems, the goal of systems is to find where the lines intersect if they intersect. So if two lines will never intersect, of course we would have no solution. So therefore, that's why she puts the no solution sign. Okay, last way that you could see it. We would have the same line. Okay, watch Ms. Delk. She's going to do one in blue, the same line. She's going to go right back over it. Okay, notice they're the same line. So they have infinite number of solutions because basically that means if they're the same line, they're hitting at an infinite amount of points on that line. Okay.
Another way of knowing same lines in upper level math, we tend to call those coinciding.
Okay, I was actually helping my 7th grader last night with homework, and that word was brought up in his directions to identify the coinciding lines. So we think you've heard that before, but it's just a reminder over these next few days. Okay, so solving systems by graphing, which is the easiest way. That's why if you've got a piece of graph paper, it might be the best way to go. You would rewrite the equation in slope-intercept form. Remember, that's y equals mx plus b. That's the form we like, y'all like, because it's the easiest for you to graph. All right, you're going to graph each line, and then you're going to identify the solution or solutions.
Which means you must write it as an ordered pair.
So every answer, see Ms. Delk, x comma y, because we hope it's going to intersect on a graph, which would be a point on the graph, meaning the solution has to be a point. Okay, first one, here we go. Notice the first one is not in slope-intercept form. It's actually in standard form. Ms. Delk is actually going to quickly solve it to slope-intercept form, so we're going to solve it for y. Okay, she's going to isolate the y, like y'all just did on this test today. Okay, she's going to do her little math here, isolate the y, and she's going to move it to transform it to slope-intercept form. And her slope-intercept form looks like it's going to be y equals negative 1/3 x minus 5. That means she's going to begin at 0, -5, and then she's going to fall 1, run right 3, fall 1, run right 3, fall 1, run right 3. She can also do the same thing. She could rise 1, run left 3, rise 1, run left 3. It's basically running slope in reverse, and y'all all know that by now.
Make sure you take your straight edge.
She's going to use her ID.
And I'm going to turn my
That's what
paper
we
for
like
just
to
a
do.
minute.
And remember, you have a straight edge around your neck at all times. So if you're like us, we like our lines super straight, because when you're doing these graphically, you've got to see that perfect point where they hit. So that's why we're going to really use a straight edge. Okay, our second line is y = -7. So you all know that line should only touch the y-axis at -7. Okay, and remember that every y value of that line is going to be -7. So that line basically says y is -7 at every single point on the line.
And that is an example of a Hoy line. So notice I drew a horizontal line at -7.
Okay, remember you're looking for the point of intersection. So Ms. Delk's going to circle that in orange. That would be our solution to this system. That means if we plugged in 6, -7 into both equations, it would balance them both. Okay? All right, second one. Ooh, she likes that. It's already in y = mx plus b, so she's going to quickly graph it. She's going to begin at 0, 5, and then she's going to rise 1, run right 1, rise 1, run right 1. Remember the opposite. You would also fall 1, run left 1, fall 1, run left 1. Okay, we do that all the way across the graph at this point because we don't know where they're going to intersect. So we're just going to run the whole graph so that we can see their perfect intersection point, if they're going to intersect. Okay, that's y = x plus 5. Now she's going to, the second one's in standard form. So you really have options, but we like you to take it to slope-intercept form just so you don't mess it up. And that way you see the slope and the y-intercept and you're looking for the point of intersection. So she's transforming it to be solved for y, and she has y = x minus 2. So she'll begin at 0, -2, and then she's going to rise 1, run right 1, rise 1, run right 1. Ooh, notice what's happening to those lines.
Doesn't look like they're going to intersect yet.
Doesn't look like they're going to ever intersect. Okay, so we can definitely see they're never going to intersect. They have different y-intercepts, but they have the same slope.
That's true for all parallel lines.
That is true for all parallel lines. Notice that. Different y-intercept, same slopes. That means they're basically going to rise 1, run right 1 all the way together, meaning they'll never hit. So if you do not have a solution, you do not have a point where they're ever going to hit, that's a no solution.
They have nothing in common.
Okay. Remember that we could also show you another kind of line that's going to overlap, but we don't have that version on here. So you'll see it this week when we start practicing.
So the first method for solving is by graphing. Now, there are times when graphing is not appropriate, such as if they were to intersect at a fraction or if you weren't provided a graph paper. So we're going to show you 2 other ways algebraically. First of those is solving by substitution.
Okay, so remember what it means for Ms. Delk and I to have a substitute come into our classroom. We're basically being replaced
For the day.
for the day, right? So substitution method is a method of solving system of equations by substituting equations within one another. Notice Ms. Delk's writing here. We've made you little notes. We're going to solve one equation for x or y, and we're always going to try to solve for the variable whose coefficient is positive or -1 because it just makes the work easier.
Because I can easily divide by 1 or -1, and that does not create fractions for me.
Okay, good. And then she's going to substitute the expression into the other equation. We're going to solve for a variable. We're going to go back, substitute into the other equation, solve for the other variable. Notice how we're solving every time for x and y.
If possible.
Yes.
So looking at this first one, for substitution, you're always looking for a variable that's completely by itself. In this case, I have 2. They were generous. They gave you 2 of them. I always like to select the first one, and I always like to circle when I'm going to be substituting. So wherever I see a y in the other equation, I'm going to substitute in 4x minus 1.
Okay, notice she's going to, that says y is 4x minus 1, so she can take the other y out and plug in what y is. Substitute in.
Now I can quickly solve for x, just like we've been doing since the beginning of school.
Variables on both sides of the equation. We all know how to solve that by now.
Hopefully.
Okay. Yes, hopefully. So she's going to isolate the x variable, solve for the variable. She's going to use division property of equality right there, and x is equal to -2. Something y'all could all do. It's on the back of the minute all the time. Okay, notice she can't stop right here. We are solving for a coordinate pair. We only have the x. So what she's going to do is use substitution property. She's going to take that x of -2.
And I'm always going to substitute into what I originally circled. You'll always see me do that because that's already solved for the variable I need. I need y. This will easily help me get that.
Okay, so watch her substitute the x in. She's going to put y equals 4. Remember that when we use substitution property, we always put it in parentheses. We do our operations, and we got y is -9. Okay, you can't leave it like that because the answer to a system, if they intersect, is a coordinate pair. These two lines, if we had graph paper, would intersect at -2, -9, and they're going to intersect one time. Okay?
Okay, let's do another one. So looking at number 2, notice how neither equation is solved for x or y. I'm always going to choose the equation where the coefficient is 1. So in this case, I'm going to choose to use this first equation, and I'm going to get x by itself. That way I'm not going to have to do any division. So I'm going to subtract 5y from both sides. And I now have x is equal to -5y plus 4.
So see how she solved for x, and that was step 1. Solve one equation for x or y. Ms. Delk solved for x, just because it was easier. So
I didn't have to do any division, no fractions. Anytime I have to do this, I always like to mark out the original because I'm no longer using it. I'm using these two equations. Wherever I see an x, I need to replace it with this whole expression. So in my next equation, I'm going to say 3x. I'm telling myself x is worth -5y plus 4.
in substitution property, you know you have to put it in parentheses. Okay, so notice Ms. Delk's writing. She put -5y plus 4 in parentheses for x. And then she's going to do distributive property. She's going to combine like terms. She's going to use, division property of equality, things like that to that's a problem.
Notice that the variables here canceled, and I'm left with 12 equals -1, which is not a true statement. Anytime when we're solving and we're left with not a true statement, we should remember that that means there is no solution.
Okay, so think about what it means for two lines to have no solution. If Ms. Delk and I ask on your next test, you did all the work for substitution and you got a no solution, that means that technically they're never going to intersect. That means that those two lines were technically parallel.
And they should have the same slope.
And I bet if you could solve for the slope of them, they would have both the same slope.
And since we're not in slope-intercept form yet, we couldn't tell them slope.
That's right. We couldn't really tell what we were doing.
So that's substitution method. Y'all can go ahead and try these two. We've done two for you. Try these two. Remember, always isolate the variable whose coefficient is 1 or -1. That way you won't have any fractions to substitute.
And tonight you've got that. You've got in both equations, we gave you both where you have a variable, a coefficient, of 1 or -1. So you can try those by yourself. We'll check them tomorrow.
The other method that we use to solve algebraically, which is of course our favorite, is elimination. We like to eliminate.
Okay.
Another definition there.
Yeah, elimination method. The definition of eliminate is to get rid of something. So our goal is to get rid of a variable. All right, elimination method, a method for solving systems of equations by adding to eliminate a variable. All right here, step 1, you're going to make sure the equations are lined up in standard form. You just had a test over standard form, so you're going to see Ms. Delk write standard form. That is ax plus by equals c. So you want them in standard form. Then you're going to eliminate the variables with matching opposite coefficients. That's a huge word in this case, opposite coefficients.
That means same number, but one's positive, one's negative.
Then you're going to multiply one or both equations to create this. That may have to happen. You may not have to do that. Step 3, you're going to solve for the remaining variable. Step 4, we like substitution property. You're going to substitute your answer into either original equation and solve for the other variable.
Okay, so let's do number 3. I'm going to skip number 1 and 2, and I'm going to go straight to number 3. Notice how I'm in standard form. I have ax by equals c. Notice that right now, neither of the variables have the same coefficient. I have a 3 and a 6. I have a 1 and a 2. That means I'm either going to multiply one or both equations. To do that, ask yourself, can you make the smaller coefficient into the larger? I can easily transform a 3 into a 6 by multiplying the whole equation by 2. However, they would be matching but not opposite. So not only do I need to multiply by 2, I need to multiply everything by -2. We're going to distribute to everybody.
That's right. Remember, if we mess with one term, we mess with all terms. Okay, that's creating, what Ms. Delk is doing right there is creating an equivalent equation because all she did was multiply everything by -2. And y'all know math is all about equivalency. We can do it if it's equivalent. So if we're multiplying one term by -2, we got to do all terms by -2.
Notice I just simply rewrote the other equation that I did not change, and I'm going to add the two equations together. In this case, the x's eliminate.
Oh.
The y's eliminate. If everything eliminates, there's nothing left. And in math, we represent that with a 0. And then 4 minus 4 is 0. I'm left with no variables, but a true statement is left. Earlier, we had no variables, but the statement left was not true, and we said no solution. Remember, if variables are all gone and you're left with a true statement at the end, that means you have infinitely many solutions.
Okay, what that means on a graph is if Ms. Delk graphed both of those lines, okay, if she changed them to y equals mx plus b like y'all would normally do, and she graphed both of them, it means they would technically be the same exact line.
They would be coinciding.
That's right. And that means they're going to hit an infinite number of times because they're hitting at every point on the line. Okay.
Okay, let's do number 4. Notice
I'm
I'm in.
the harder one.
Yeah, I'm being nice. I have standard form ax by c. I always ask myself, can I take the smaller coefficient and make it into the larger? If yes, that means I only have to multiply 1. If no, I gotta multiply both. There's no way for me to multiply 5 to become a 7. There's no way for me to multiply 9 to become a 10. That means I'm gonna have to multiply both equations. I always choose to eliminate the variable that has the smaller numbers. So I'm gonna choose to get rid of the x's because 5 and 7 is much smaller than 9 and 10. I'm gonna choose to multiply by +7.
Notice that she would have 35x.
And
so
by
she
-5.
needs the opposite. So notice she's going to have negative 35x. Remember, you need opposite coefficients.
Notice that when I did this, I multiplied it to everybody in that equation. That's something that y'all tend to miss. That's probably the most missed thing for y'all. You'll do it to one, but you won't do it to all. So make sure you're cautious when doing this step.
Remember that you're creating an equivalent equation by multiplying every term by -5 right there.
Okay.
She's ready to add them.
The x's
watch
eliminate.
what's happening. Good.
I've got -13y is going to be equal to -65.
All right, she's just adding. She's using
Rephrase.
the signs of the numbers.
That's a +13y.
Oh,
My bad. Sorry.
She's using the signs of the numbers to combine them. Now she's going to use
62
division
minus
property of equality. Divide both sides by 13, so y is going to be -5. Okay, she's not done though because every system must have an ordered pair as its solution unless they have infinite amount of solutions or they have no solution. So she has to get the x value too.
And I could plug it into technically any equation. I could plug it into the ones I created, or I could plug it into one of the originals. I tend to plug it into one of the originals because these are smaller numbers. And I would probably choose the top equation because 5 and 9 are smaller than 7 and 10.
That's right. We kind of work to the smaller numbers because y'all are great if we can keep numbers small. Okay, watch her substitute in for y. She put it in parentheses. Remember, substitution property, what we put in, we have to put in parentheses. She's doing the operation, so she's multiplying 9 times -5.
And the addition
doing a
property.
two-step equation, using her addition property of equality, and she's fixing to use division property of equality. And so she got x is 7. All right, notice she has an ordered pair, but she can't leave it like that. She must write it as an ordered pair. We keep telling y'all math is all about the details. So the answer to this system would be an ordered pair. Means if we graph those two lines on a coordinate plane, they would intersect at 7, -5. You could also check that algebraically by plugging in 7 for the x, -5s for the y's,
And they should
do the
be
math, and they should equal -10 and -1.
That's the great thing about systems. You can always check your answer by plugging it back in.
Okay. So remember, this is just a quick review of systems from 8th grade. We're getting ready to graph systems of inequalities
next
which is the fun part. So, okay, let us know if you have any questions tonight or tomorrow, and we'll discuss the two that we didn't do on each page.